Okay. 2.1 rates of change and limits, day 2. We are looking at a lot of laws today, so getting ourselves a lot of laws written out here. Our property of limits here, let me explain what's going on. Given the initial conditions at the top here, the limit as this function f, as x approaches some number c, has an answer that they're calling L. The limit of this second function g, approaching the same number, has an answer of m. And we use this to kind of show the breakdown here. If I were then to take the limit of those two functions being added together, what my limit properties say is that I actually can take the limit of each one individually and add their answers. Notice it's going to be the same thing. If I have a plus here, it's going to match what I do between those two answers. If I was adding the functions, I add the answers. Same thing for our difference rule. If I'm subtracting two functions, I really could do the limit of each one individually and subtract the results. Similarly, when we get to product and quotient, multiplication and division, same information at the top. I can then do the limit of each function individually and multiply the results for a product rule. I can do the limit of each function individually and divide the results or the answers for the quotient rule. The only thing you have to be cautious on that one is it does have that little restriction. We can do that assuming the limit of g of x is not 0, because obviously we can't divide by 0. I had a question earlier, does that mean that this limit does not exist if the limit of g of x were 0? Not necessarily, but we might have to do something like look to simplify. We can't just do the limits individually and divide. It just means we might have an extra step, potentially. Constant multiple rule. If I have a number multiplying my function, I could just take the limit of the function and multiply the answer by that constant. An example of what that could look like. Okay, that 5 would be like the k in this situation. And really, I could then just take the limit of x and multiply the result by 5. It's like a constant can slide out front and wait till we've taken the limit of the function. The power rule is just like it sounds. I can do the limit of the function, which would be the limit of this, and then raise it to whatever exponent is outside of that. The only thing we need to be careful of there is that it doesn't necessarily have to be handed to us as an exponent. For example, remember your algebra rules and how we can reformat things. Something like the limit of the function cube root of x could fall under this power rule if we wanted it to, because I could rewrite cube root as x to the 1/3, right? So sometimes they look like, and depending on what we're doing, we may want to rewrite it in the other option of a format, because then I can do the limit of x and raise my result to the 1/3. So just remember your options for all the different ways we can rewrite things to make things easier. All right, so applying some of those. Let me do this first one, and then you guys can finish up the rest of them. It gives us at the top some information. The limit of f of x as x approaches c is 7. The limit of g of x as x approaches c is -3. And they give us the first question, the limit of f of x plus g of x as x approaches c. All that means is we do the limit of each one individually and add, because that's the symbol between them, the results. So the limit of f of x was 7. The limit of g of x was -3. Our answer would be 4. Okay? Go ahead and use our rules to finish out B, C, and D. you're done, just glance at your table partners. Make sure you guys have the same answers. Moving down to B, that is our constant multiplier. That just means I can move the 4 out front 4 times and then do the limit of G as x approaches C, which is -3. Should get -12. Moving over to C, our product rule says I can take the limit of each one individually. So of F was 7, of G was -3. We should get -21. And then our division, each one individually, our quotient rule. Limit of F was 7, limit of G was -3, and I would leave that as 7 over -3. Any questions on our rules here? All right. Continuing to look at problems like this and addressing our algebra. It's all about the algebra on this. I see this problem, limit of 2x plus sine x over x as x approaches 0. Again, we're asking to do a limit. The first thing I would always try is, can we do direct substitution on this one? No, not an option, right? Because I cannot sub in 0 to the denominator. The other thing that jumps out to me on this one is I see that there's a sine x in the top and there's an x in the bottom. So that triggers my, ooh, can I rewrite this as sine x over x? We can, we just have to be careful. Can I just break it right here and call this 2x plus sine x over x? No, remember we just talked about at the beginning of today, can you just break it at a plus or a minus? No. So if I were to break that apart, does anyone have an idea here? What do I have to do to be able to break that into a sine x over x? Can I break them apart? Multiply? What would I multiply? Sheldon? Like terms? Oh, like a GCF? Agreed. We did that earlier, right? We factored out a GCF. Problem is in the top, this is not multiplication, right? Because that's within the sine function. So it's not something I can factor out. I want to pull apart that 2x and that sine x, but I can't just break it. Yeah, common denominator, right? That's how those two would have gotten put together to begin with. If I'm going to break apart a fraction, I can do that as long as they both continue to have the common denominator, right? I can break it into the two separate fractions. I'm not going to actually do anything when I rewrite other than it's just a different format, right? I'm just rewriting that same exact fraction, breaking it back into what we probably would have added together because they had common denominators. I've pulled apart the fraction, and now it's 2x over x plus sine x over x. Now, would I ever write 2x over x? Simplify that, right? That is just 2. So we can use our limit laws at this point. And that says that I can take the limit of each one individually, right? And add the results together. Okay, I'm going to talk about this first one because we really haven't had a rule to specifically say this, but think about this. 2 is a function, right? And if I'm supposed to do, can I do direct substitution to 2? Is there any domain restriction there? No domain restriction, right? I can plug anything into that function, but if I plug it into the function 2, what am I going to get? 2, right? There's no x there. Nothing's going to change about it. So the limit of 2 as x approaches 0, doesn't matter where x is going, it's going to be 2, right? Nothing's going to impact the number 2. Okay, how about this one? Sine of x over x as x approaches 0. 1, we should know that one. Add our results together. We get 3. Questions on that? We've now seen that same problem like 3 different ways as ways we can manipulate, right? We had sine squared and we broke it into sine times sine. Then we had a GCF of x that we pulled out, and now we're looking at breaking apart fractions using common denominators. Here's one more way that we're going to see that same topic show up. Again, we see that limit, we see a trig function, we see an x in the bottom of the fraction. So again, you need to be thinking that whole sine x over x. That's kind of where we're always headed with these trig functions and an x. I don't even see the word sine in this problem. Could I see the word sine in this problem? Yeah, what is tangent in terms of sines and cosines? Sine over cosine, isn't it? So we could use our trig identities, which, yes, we're going to have to brush up on our trig identities. We could use our trig identities to rewrite tangent of x into sines and cosines so that I can see a sine x in here. So instead of tangent x, I could write that as, that says tangent, right? Now, some of you are going to want that still to be in the numerator, so I could put the x there. Dividing by x would be the same thing as multiplying by its reciprocal. So instead of doing that, I could just multiply by 1 over x. The x is still in the denominator, right? This still says tangent x. So it's still the same problem. It's still tangent x over x. But again, I could just slide that sine x. Here's my sine x over x. And the other part I have is 1 over cosine x. So I'm looking at if I just, again, I haven't done anything yet. Oops, 1. That's my two fractions, right? Sine x over x and 1 over cosine x. Okay, now, we know the first part. Limit of sine x over x as x approaches 0. I've seen that, what, 4 times today so far? Let's talk the second part. Limit as x approaches 0. 1 over cosine x. Can I do direct substitution? Well, the question is that making the denominator 0? What is the cosine of 0? 1. The cosine of 0 is 1. Do you need to remember that? Yes. We will continue to brush up over the next couple weeks on our unit circle values. But yeah, we need to remember that. So cosine of 0 is 1. 1 over 1 is 1, and 1 times 1 is 1. Any questions on that? All right. Now we're going to go to some visual limits. Again, some of you, depending on where you're coming from, are going to have a little bit better foundation on this than others. But these are what are called one-sided limits. And when do I know it's a one-sided limit? When the number we're supposed to be approaching has a little plus or minus in the exponent area. So a little superscript of a plus or a minus. What is that telling me to do? I'm supposed to be approaching this number, but whatever this is, so this is plus, that tells me that I'm going to start my pencil to the right of that number. And only right. So I will start my pencil to the right of that number. I will start tracing to that number, and whatever I get when I get close to that is my right-handed limit as x approaches whatever that number is. If it were a minus sign that's up in my exponent, that means to start left of that number. Questions? Okay, so this is a very simple graph. Let's say that number happened to be like -1. So I'm supposed to be approaching -1. And if it had been written as x approaches -1 from the right-hand side, I will take my pencil, I will move it right of that line. Wherever I need to get on the graph, I will start tracing towards that graph. And as I approach that x value, this line right here, of -1, I finish the statement -1, comma, what point am I heading towards? And we would say -2, right? Or if I were to be heading to it from the left-hand side, I would have literally put my pencil left of that line, trace my graph, and as I get close to that line, I would finish the ordered pair, -1, comma, whatever we are approaching. These happen to match, and they would both be -2. Questions? Let's look at some that don't always match. Okay. So, given this picture, The whole picture over there is what's called f of x. So as it's referring to that, it's referring to your picture when it says limit of f of x. So it asks us to do the limit of f of x as x approaches 1 from the right. Second one is as we approach 1 from the left. And then the last one, I tend to call it your generic limit or general limit at 1. Okay, we'll talk about that in just a second. So this is the line we're headed towards. There's x equals 1. The first one tells me to get on the graph at the right. Now I know there's a lot of stuff going on at the right, so I don't get distracted by all that stuff, but I'm just going to kind of start right, trace my graph here. So I'm tracing, 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 and I start getting close to the line, and I want to finish the statement 1 comma, what are we getting close to? 1. 1 comma, this point would be 1 comma 1, so my answer would be 1. So second one says start left of that, anywhere. It doesn't matter where. Start tracing, and as we get close, we slow down and answer the question 1 comma, and this point would be 1 comma 0. So our answer would be 0. Now, the last one is your generic limit. Your generic limit is going to completely be based on the answers to the two that we just did above. These two right now do not match. Right? If they don't match, you do not have a limit at that number, a generic limit. So I would answer down here, does not exist. If those do not match, I don't have a limit there from both sides. If they did match, let's say that had been 1 and that had been 1, if they do match, you do have a limit, and it is what they match at. Okay? All right, we're going to build on that, but I'm going to let you guys try to build on it yourselves. So, same picture with your table partners. I want you to find the right-hand limit, left-hand limit, and generic limit at 2, and then that last one, function value. When you have answers, compare with your table. Okay. We are heading towards x equals 2, which would be this line right here. First one says put my pencil to the right of that and start tracing towards 2, and then slow down and answer the question 2 comma, this point would be 2 comma 1, right? So our right-hand limit would be 1. Left-hand limit, again, there's a lot going on. You don't have to start this far away and jump or anything. I just need to start to the left, start tracing, and as I get close to it, it would again be 2 comma 1, right? So this is what we didn't see on the last page. Now these match, right? And if they match, we have a general limit. Notice no plus or minus there. So if they match, I now have a limit, and it is whatever they matched at. Questions? Okay, function value, f of 2. What am I looking at for f of 2? What do I look for? Yeah, a point, right? A closed dot. When we get down to function value, which is this notation, you are this is when closed and open means something. Does closed and open mean something up here? Not at all, right? But now it does. So I'm looking for my closed dot, and it would be up at 2. So again, we're finishing the ordered pair, but it is 2. I would tell you right now the most commonly missed one is probably this one, saying that it does not exist because there's an open dot there, right? The limit as we approach 2, we want to say doesn't exist because there's no a closed dot here. But the open and closed has no impact on our limit, has an impact on our value. Questions? All right, last little part here is you doing your own picture. So our own picture requires us to remember how to graph a piecewise function. And again, you guys are all coming to me from different pre-calc classes, so different methods for this. I'll give you a second to see if you remember how to draw piecewise. And then we are basically back to what we were just doing on the last page, looking at our piecewise graph to answer the limit questions. All right, different methods for different teachers that teach piecewise. Some of you use tables. Some of you like draw the graph and then erase to just the domain that it's supposed to be at, whatever it is. But some of these we need to talk about too. What does that graph even look like? First one, f of x equals 2x plus 1 for x is less than 0. Remember, less than, greater than, or equal to impacts our first dot. So we're starting at 0. We're going less than 0, which would be graph to the left of that. At 0, this would want to have a y-intercept of 1. So we're going to have an open dot at 0, 1. It has a slope of 2, which moving left, I'm going to kind of go the backwards way, down 2 over 1 here. That would have been that top graph. Your second graph, that's f of x equals 3 or y equals 3, but it's only at x equals 0. That is literally 1 point, 0, 3. So we should have a closed dot up at 0, 3. And your last one, again, y equals or f of x equals 2 for x is greater than 0. So at 0, we've got that open dot. That is, again, a horizontal line, y equals, like we talked about at the beginning today. Open dot, horizontal line this way, and then use that to answer my questions below. Going through those real quick here. Limit as we approach 0 from the right-hand side means we're going to be using this red piece of graph. As I approach, I'd be approaching 2. As I approach from the left, I would have been approaching 1. As I grow here, I would have been getting close to the y value of 1. At 0, because our right and left hand do not match, we do not have a limit, right? They don't come together. There is no limit at that value. Does not exist. And the function value is our closed dot. At 0, our closed dot is up at 3. So you can see that I could have 4 different answers all at the same x value. Any questions? All right, your assignment, again, out of the book, page 67, 43 through 49 odd, 55, 57 through 59, 71 through 76. If you need your online book, it is still on the board there, so you can navigate to that to get the PDF of the book.